some time then for us to start the next chapter, functions of several variables, and so that will still be on the test list up to the end of the week. Okay. All right. So the helix and the parking garage ramp is what we're talking about right now. So the picture in the middle is supposed to suggest that we have more room for curve, even though it is kind of a circular, but there is more room for it inside of that cylinder, and that is why the helix on right will have lower curvature than the circle that is the base of the cylinder. Okay, and that is why the turning circle could be larger than the radius suggests. So we want to demonstrate that, and so I go back to, so we'll do the algebra later. Let's start with the with Excel. Okay, so this is a circle. Okay, circle. Let's make it circle. One. Okay, so it's a circle. It's a two-dimensional curve, and I think, let me see if I have it here. Here it is. So unfortunately, Excel doesn't do 3D. So this is best we can do is some kind of homemade spreadsheet that actually does plot 3D curve, which happens to be the helix, and you could have various well, you can move it around just to see, to confirm that it is what it's supposed to be. Okay, so as you can see, you can turn it. Okay, so that's the just an idea of what the helix is supposed to look like. So it's a circular, but there is a ascent there. Okay, so the question then, where is that circle? You know, there is some circle here. Remember, circles approximate our curves, and then the question becomes where that circle is located. It is not, I don't want to leave the impression that maybe the picture in the middle suggests that the circle might be, might have a slope. It doesn't have a slope. It is, well, we'll see it. It actually is still horizontal like this, except it just happens to have higher radius, or higher radius. Okay, so let's do the other Excel. So we will not be able to plot it, but all the computation is still applicable entirely. Remember, that's the advantage of vector analysis and vector representations, that these are our formulas. There is no dimension there. No dimension is applicable, including finding a dimensional space. We can still study curvature of curves in that space. They're just exactly the same manner. Okay, so now we just move to dimension 3. This is the curve, and now what do we do in order to replace this circle with a helix? And the answer is simply add the third column. Wherever I have x and y, I'll have the z as well. Okay, and then that's all the work entails. Okay, so let's do that. Okay, so as you can see, it is parameterized the usual way. So radius, well, it's not the radius, but let's say let's make it 1 again. It is supposed to be 1 over here. Okay, so well, incidentally, this is the this is supposed to be the curvature, which looks nothing like it's supposed to. It's supposed to be equal to 1, and it is. Look at it. There is virtually no change. It's just Excel resizes in such a way that fit, so you can see the graph, all the features of the graph, but really it oscillates between it is at most 1,000 differential between the values of the curvature, and it's not surprising that it's not exactly 1, because after all, it's made of points. It's not an actual infinitely accurate, perfect circle. Okay, so we'll see about that. So what we're going to do is I'm going to add a column here for to accommodate z. Okay, accommodate z. So I'm putting z over here, and then what remains is just to draw enter the formula, which is actually is very simple. It is. I don't think I provided actually the formula, so okay, let me do the formula. The formula for the helix. I think I did, but that's just as well. So circular, x is circular, r cosine t, or sine t for the x and y, and for z it's simply t, or maybe a t with a coefficient if you want to stretch it vertically. Okay. So that's my helix, and so then I have the first two columns taken care of, and now I just need z. Okay, so let's do that. So I'll just enter. I think I'll put some kind of r here to indicate how fast the parameter is, how fast we are ascending. Okay, because you can like just like a spring, you can have it contracted or it can stretch. Okay. So we are entering then, I will write it is equal to my coefficient of this one, which is R6, C6. Okay, so that will be my parameter, and I multiply by time, which is this one. That's all it takes. Okay, so I have my naturally starts at 0, then I spread it out all the way down. So, and I have my helix. Unfortunately, it is a helix only inside of our minds. I cannot plot 3D, but you can imagine that this is on right. You have x, and y, and you imagine that there's actually an ascent there, and that's the third parameter. Okay, now y prime, that's easy. Okay, so I'm entering one more column for z prime over here. There is no trouble whatsoever to, there's no need to compute in any particular way. I just spread it to the right. Okay, so what do I have here? If we look at it, it's the same difference quotient. As you can see, the change of z divided by the time increment h on left. Okay, so at this point, then I spread it down in order to get the z prime. Okay, naturally, look at it, the speed is 1. It is the same number as this r over here. Well, so we knew that. Now, the speed is not right. Okay, so its speed is 1, maybe, but maybe not. The speed that came from the circle. So the speed right now is the speed with respect to x and y. So it's in other words how fast we're moving on a circular fashion in the xy plane. Okay, so what do we do? How do I fix this? The formula for the speed.
Do we divide the oh yeah, we divide the cosine argument t by r? Like the
it might work, but the more direct way is use we have z prime, so we just need to incorporate z prime into our formula. I have already x prime, y prime is there, so z prime is missing. So I'll just add z prime, meaning z prime squared. So over here I will just add plus this thing, the z coordinate squared. So squared. Okay, so let me spread it down and we'll see what the things look like. Okay, so as you can see, we are going faster because there is an ascent. In addition to rotation, there is also an ascent. So as you can see, the number has changed, and it is, you can guess it is square root over 2, like this. Okay, so it is because it's 1 horizontally and 1 vertically. So that adds up to square root of 2 over 2, the diagonal. Okay, so now we need t, the unit circle, unit tangent vector t. Okay, so we're doing the same thing. I am once again inserting another column. This is going to be Z. Okay, and then I just spread it out to the right because the formula is the same. As you can see, look at it. Why is it negative? Okay, because it's divided by the wrong one. I have to divide by this one. Okay. By the speed. Okay, so once again, it is simply the z coordinate of my f, divided by the blue one, divided by the speed, which is in the next column, the red one. Okay, so that gives me the whole thing. It gives me the z component of my velocity of my t. Okay, so as you can see, it happens to be constant, as to be expected. It's just the same. If the direction is positive, direction is up, then it is just, all we do is just resize it. What is this? I forgot. What is this? Okay, so the next step is the coordinates of the t prime. T prime. So that is the. Let me just show you the formula again, where everything is here. Okay, so t prime, the magnitude of t prime we were to compute. F prime we already have found. That's simply the speed. That's, we have a column for the denominator. The numerator right now only has 2 columns for x and y. Now we need to also find over here, we have 1 more column, and then we'll have the curvature. Okay, so I'm inserting. So this is once again x, y, z. And well, I need a z too. Okay, z. Okay, this is z. And then difference quotient is applied again. Same matter. Okay. Okay, let's see. Okay, I got a bunch of zeros. What does it tell you? Can you explain it?
Motion in the z-axis is linear.
Linear, right? So linear motion, no acceleration. That you have naturally you have that this thing equal to 0. And now the curvature is computed now with everything as we have. The magnitude of t prime still missing 1 variable from z. Okay, so once again I do what I just did. I will add the z coordinate, z component of my t prime into this into the numerator. Okay, so that is plus this value squared. Okay, that should do it. Okay, let's see. Okay, so well, that is pretty much it. So what does this number tell you?
It has to be a circular line, and it's not a line, so it's a circle. Well, I mean, the curvature is constant.
The curvature is 1/2. What does it tell that? What tells you? What does this tell you?
That the curvature is constant.
Yeah. Well, yeah, it is constant, as a matter of fact. Yes. So which is interesting because the only constant curve on the plane is either straight line or a circle. But since we step up from that, we can there's another one. But a specific number, 1/2. What's the significance of it?
The radius of the curvature is 2.
Radius of curvature is 2, even though our circle, look at it, has radius 1. Okay, so the helix has half the curvature. The standard helix has the curvature half of the circle of the same radius. Okay, so in other words, of the base of the helix is the circle, and that circle it has a curvature twice as the helix itself, as we just roughly suggested that. We just didn't know exactly the exact number, but as you can see, it varies by 2, by a factor of 2. I could certainly verify this, and if I start ascending faster, what's going to happen to the curvature?
It's going to decrease.
It will decrease, right? The spring, we're spreading the spring. Well, it's not tech. No, I think Is it fair? I think the spring, unfortunately, the metaphor doesn't work because the spring also gets the radius declines. It shrinks a little bit when you stretch it. But imagine that it's like a cylinder. No, I can't think of anything that behaves like that. How this spreads out, so there's more room for it. So if I put a 3 here, as you can see, what happens is the curvature becomes 1/10, and on as you spread it. Okay, so that's we have. Well, let me give you the formula. I'm not going to derive it, but the formula for the curvature of the helix, for the standard helix. Okay, so what we had is, it seems like it is a half, but there is a more general formula. Okay, the formula is kappa is equal to 1 r over r squared plus 1. Okay, so indeed, if r is equal to 1, then kappa of the curvature of the helix will be 1 half. Okay, so that confirms it. And you can see how increasing, so it is slightly different approach here with this formula is the opposite. We are changing the radius while we keep the rate of ascent the same one, but we can change the radius. And you can see if I keep increasing the radius, what's going to happen. If r is going to infinity, what's the limit?
0.
Yeah, 0 as r goes to infinity. And in the meantime, what if r goes to 0? Where does this one go? R goes to 0?
Okay, that's 0.
Yeah.
Why doesn't t, if increasing the rate at which, if we had t squared at the end instead of
Well, why t? There's no t here. It's constant curvature, so it does not depend on t.
Oh, okay.
So yeah, so that's the thing about helix is that it has constant curvature. Yeah, I don't have other examples right now. So you can certainly think if you could pick a curve at random, it will have variable curvature. Okay, as we have seen already, even on the plane. So r goes to infinity, it goes to 0, r goes to 0, it also goes to 0. That's kind of surprising. So I can see how it is getting wider, so you can imagine how this thing becomes wider and wider with the same height, the same degree of ascent. It becomes wider and wider, and it certainly becomes flatter and flatter. So the circles become smaller and smaller, and larger and larger, and therefore the curvature is going towards 0. But turns out when you have it smaller and smaller. Yeah, can you explain the second? The first one is because the radii, it's the radius of the underlying circle has become bigger and bigger, and the ascent is certainly not noticeable in comparison with. And can you explain this? When the radius is going towards 0, what's happening to the helix?
It's becoming more and more like a line?
Yeah, that's right. It becomes more and more like a straight line. So forget about the swing. The swing is so small in comparison to the ascent that it's almost a straight line. Just like as I said about the stretching a spring. You stretch a spring. This is what we're doing right now. We're stretching a spring, and the radius becomes smaller and smaller. So the ascent then becomes overwhelming. The ascent becomes what determines the shape of the curve more and more, and therefore the curvature disappears gradually. Okay. Okay. So the specific part that remains. So this is just a formula. I'll give you another formula. This is general formula for the curvature that whenever necessary you can use to compute it. So the curvature is F. Well, I don't have a formula. Sorry about that. Anyway. Yeah. So right. So the formula relies on the cross product, and we skipped it for the time being, so I cannot give you that formula, unfortunately. So anyway, what remains here is establish some specifics about where's my picture? Okay, where that circle is. So it does seem to suggest, the picture itself suggests that that circle has got to be horizontal, but also horizontal. So the circle that approximates our curve at this particular location, okay? So it appears to be, just from, kind of qualitative analysis of what we see, appears to be horizontal, and we also know that the radius is 2. Well, if this radius is 1, the radius of this circle will be 2. So, which means, by the way, then the picture is not good. That's what it means. Because, as I said, it has a radius of double. So it will be like this, and you can guess where the center lies actually on the opposite end of the helix. So this is the circle, and this dot over here, the center of that circled curvature lies on the opposite edge of the surface of the cylinder. Okay, so that certainly can be demonstrated, but let's start with this. Okay, so this is what we're talking about. We're talking about our curve, could be helix or not. Tangent vector, this could be in any dimension. What we know also, it is a unit circle, remember, and as a unit circle, it means that its derivative, because it's unit vector, its derivative will be perpendicular. Okay, so that will tell us where that circle lies, because we know that we know t, and we know the. Then, if we know that, then we know the direction of where that our circle lies. The circle of curvature. That circle of radius 2. So there's a circle here somewhere. Well, some big circle. And center here somewhere. So the blue one, or the, let's say, the green one, well, it somehow behaves. So this is my helix, or another curve. Okay, the tangent vector, unit tangent vector is t. Okay, and then we're looking at one point and want to find where that center of that circle lies. It will be certainly on a perpendicular line. So we already know what the direction of that line is. So once again, we have that theorem, t is equal to is fixed, then it means that t is perpendicular to t prime. And t prime, remember, it's the numerator of the fraction of the curvature. Okay, so one thing that comes up, let me find that place that we discussed. Yeah, that's here. So the very last formula, or the maybe not. Which formula I have in mind? Oh, early on. The there was a where's the change of variable? Oh, okay, this is it. This is, no, that's not it. Oh, here it is, in red over here. So the how to find the arc length parameter, that is the formula. It is like a differential equation for how to express the new parameter, arc length parameter, in terms of the old one, t. Not much. You just take the magnitude of the velocity, and that is your function. Even though you remember we had a little bit of struggle with that when we had accelerated motion along a straight line. It is very easy whenever you're moving with a constant speed, that is just a constant, it's easy to solve, and your relation between s and t is just a linear relation, but in general it is not. So let me write that again, ds dt is equal to the magnitude of f prime. Okay, so what I can do with it, how about integrate over t, naturally over t. So What do I get? What do I get on the left?
Yes.
S, okay. And on the right, it's just the integral. So I want to intentionally put it in the form of a definite integral. So say from, say, A to T, f prime u du. So as you can see, I flipped here the variable, I changed to u in order to not to be, so there would be no confusion between the variable of integration and the variable t, which is what s depends on. Okay, so s depends on t. The integral is ab, on which we are studying this curve, the domain of our parameter curve. And so I integrate from A to T, which may run from A to B, and then we end up with this integral, which is at this point should be familiar. This integral?
It's the arc length.
It is. Can you explain in case of it was discussed in calculus 2 for graphs, right? So like if you have y equal f of x, say, right? So well, let's make our way to this formula, or from this formula to the formula that you had in calculus 2. So how? So this is this one is it is actually a new parameter, arc length parameter. Remember, that's what S is, expressed in terms of this integral, in terms of the old parameter t, and the formula for the parameter curve f. Now let's connect it to calculus 2 arc length formula. Well, if you don't remember, that's fine. Let's just start with the graph. So suppose our parameter curve is a graph. Okay. So what's f capital? So we'll try to figure out what this formula produces. So, and then we'll have the old formula. So what is f capital?
Is that the antiderivative of f of x?
No. F. I'm talking about. I think we're not talking about the same thing. This is what I'm talking about. P is equal to f of t, and dimension is equal to 2. Let's make that clear too. So it's a plane curve. P is equal to f of t. P is a two-dimensional point or vector. F is our parameter curve. T is the independent parameter on the interval AB. So if our curve is given by the graph of a function, remember how we represent it as parametrically.
Oh, sorry, I didn't hear the use of parabola. So just t squared. It's the vector t squared. F of t is equal to the vector t squared.
F of t. That's what I'm after.
And we want it to be a parabola.
No, not parabola. I didn't say parabola. No. Just any curve, f. Any function y equal f of x, and I want to represent it as a parameter curve. How do we do it? If you remember it, maybe in a while. How to parameterize the graph of a function?
T f of t.
T f of t, right? T f of t. Okay, the standard way to parameterize it. So x is t. That's the simplest choice. Okay, so now f prime, easy, 1 f prime of t. Okay, the magnitude of that, 1 squared plus f prime of t squared, square root. Okay, so at this point, I hope you can see now that the formula is already getting familiar. So length of the curve is the integral from a to t, 1 plus f prime of t squared, square root dt. Well, I mean, we have used u here. Okay, that's fine. du. Okay, like this. Okay, so that is the old formula from calculus 2, how to compute the arc length of of the graphical function. This is the formula. It was proven with the approximating. Remember the curve? You approximated with like this, with segments on the xy plane, like this, and then naturally set up the Riemann sums, and then the limit is equal to this integral. So we could do the exact same thing with the original function also to justify that the formula that we end up with for the arc length parameter s, in fact, nothing more but the arc length of that parameter curve. So a little bit more work to be done, but the advantage is that it is this one is n-dimensional. N-dimensional, and naturally it equally applies to circles. Helix is not; it doesn't have to be the graphical function. So that was just worth mentioning. Okay, so furthermore, so let's proceed with this. ds dt is the magnitude of f once again. Okay, so which is b of t. Just for convenience, I want to emphasize that this, what we have on the right, is nothing but a numerical function, and the numerical function of speed. The speed as a function of time. Okay. So then, once again, this is what we did previously. We did the chain rule from that equation that was the relation between s and t. So t prime is equal to dt ds ds dt. Okay, so we're already doing what we have done. Times the then we take the norm of the magnitude of this in order to conclude that norm t prime, magnitude t prime, dt ds, magnitude times ds dt. Okay, so dt ds, as we know, is the curvature, and ds dt is b of t for the new notation. Okay, so that is the formula that is going to be used now. Okay, so this is the formula. So what is it? This is actually the number that we have been talking about, that we computed with a spreadsheet or approximated. It is a function, in fact, a function of t, and as I probably should put it everywhere, because kappa depends on t, the unit vector depends on t. It is the numerator of the fraction that we're looking for, right? So for when we're looking for kappa. So this thing we evaluated in our spreadsheet. The magnitude of t prime. We didn't actually compute. This is t prime. These are the three columns, and then you take the magnitude, and that gives us the fraction that the expression that we just got. Okay. So let me just state it. Well, we already stated it. Now the next step is the derivative of t. Okay, so this is the definition we're going to use. Remember, we are still looking for the center of that circle. So use the unit normal vector. So as you can see, perpendicular orthogonal. That's the third word that we use for that, the same meaning. Of t is equal to f of t. Once again, what we just discussed, remember that t is a unit vector, which means that its derivative will be perpendicular to it. So t prime will be a normal vector. T prime is a normal vector, except it's not a unit vector. So if you wanted nothing but direction towards that center of that circle, you divide by its magnitude. Okay, so the normal vector in addition to the tangent vector. So if we have our curve, then we had that picture a little bit sometime before. Unit tangent vector naturally remains tangent, and it is tangent. Okay, and then there is also unit vector, but it is this time it is also unit vector, and it points in the direction of the turn. Okay, so in here, for example, it will be pointing in the opposite direction. So then the point of this is to take that formula in green and express it in a vector form, rather than in the scalar form. So then t prime is equal to the kappa times the speed times the unit normal vector. Okay. So once again, let me have this picture. So if we have our tangent vector this way, unit tangent vector, then we have perpendicular to it, we have our normal vector, and then if we multiply it appropriately, then that's what the t prime might be longer or shorter, we don't know, but that's what it looks like. Let's suppose it is shorter. Let's suppose it is longer. Okay, so now let's carry this out for the helix, the plan and the formula for n. Okay, so helix again. So f of t is once again, let's take the easy one. The standard helix with the radius 1. Prime of t is negative sine t cosine t1, okay? And then t is, the magnitude is, or v of t if you like, is the magnitude of this thing, which is sine squared t plus cosine squared t plus 1, okay? Which is square root of 2, which is what we saw. Oh, it was square root of 2. I thought it was square root of 2 over 2. So that number is this one, right? This is the speed that we found. It is square root of 2. Yeah. Okay. So then take the unit vector. Unit tangent vector, it is simply f prime divided by square root of 2, so it will be literally 1 over square root of 2, negative sine t, cosine t, 1. Okay, unit tangent vector now, doing the, differentiating one more time, 1 over square root of 2, negative cosine t, negative sine t, 0. Okay, so we're doing what we did, we're doing using the calculus 1 skills of differentiation. We are doing it the same thing almost as the spreadsheet did, except now it is accurate rather than approximate. So those who were average speed, average velocity, average velocity, average speed, average acceleration, and this one is precise, or instantaneous velocity and instantaneous acceleration. So that is our t prime. And now the magnitude is 1 over square root of 2, and we have cosine squared t plus sine squared t square root, and we have 1 over square root of 2. Okay, and so now what the normal vector is, a unit normal vector will be pointing in the, so once again it's t over t, t prime over t prime magnitude. Okay, so it is simply this, negative cosine t, negative sine t, 0. You can confirm that it is perpendicular to t. Okay, so that is the step, going back to our picture here. this is the step that we want to make in order to find the center of the, so we have the direction, n gives the direction. Now what's the length of the step? The length of the step is the curvature, which we already know is equal to 1/2. Curvature, no, the curvature is 1/2. The radius of curvature is 2, so the length of the step is 2. So once again, let me have this picture. So the point we're looking at, so this is f of t, this is where we are. Okay, so let me reproduce the whole picture. T, and then unit normal vector, and then we go in the right direction, like this. The length has got to be 2. So this is length 2. N is a unit vector, so all we have to do is just to multiply by 2. Well, first of all, let's look at the 0. What does the 0 tell you about the vector?
It lies in the, doesn't have any z component, it lies in the plane?
It's xy plane, right? So that is, as promised, that vector is horizontal indeed, and so the plane will be, it is turning, but not in any kind of weird way. It is still turning, the turn is still horizontal in that sense. So, and then we're making the step 2. So the center is f of t plus twice n of t. Okay? So f of t where we are, this is f of t right here, and then we take a step, and then t multiplied by 2, that's, so direction is n of t, and the length is 2. Okay, so that's all we have to write out. Okay, so f of t is where my f of t cosine sine t sine t, t, plus twice my normal vector, negative cosine t, negative sine t, 0. Okay, just adding them together, we have a negative cosine t, yes, negative sine t, and t. So, well, with the answer we already knew, right? We already knew that since the radius is double, so back to this picture, the radius is double of the radius of the cylinder, which means that we end with going straight at the center of the cylinder, which means that we pass the center of the cylinder and then cover the same distance and end up to on the opposite end of the cylinder. So like this. This is our trip, unfortunately, in the mirror direction. So if we point on the right, we make 2r step or 2 step in the direction, we end up on the opposite end. Okay. Okay, so this is just one example. So there will be in the homework there might be a little bit more examples like that. So the formulas are certainly will take time getting used to, but there is really no extreme complexity here. Once you get comfortable with the ideas, the formula is really not that bad. Okay, so to wrap this up, the business about curvature is I want to say that so we can study curves, and I think we have a good reason to study curvature of curves when we're building anything. Okay, either it is a highway or it is a ramp in a parking garage. Also, if you know the more kind of a scientific sense, so we are studying a curvature. What might not be clear from this analysis is that we are talking about the intrinsic property of curves. Intrinsic property. The curvature is an intrinsic characteristic of the curve. What does it mean? It means that it's not like there's a curve and then to find out the curvature we would have to do measurements like you have a literal curve on the table, and you take a measuring stick and start measuring things. So this distance and that distance, we don't have to. The original definition tells you that it is the rate of change of the unit tangent line as it is when the parameterization is arc length. Suppose we're living inside of this curve. We could figure out its curvature by simply traveling through it. So you can simply imagine that's a tube, and there's a bug traveling through that curve. And if the bug is traveling at a constant speed, then it will recognize the turns, because that's where they will feel like its acceleration, and acceleration feels like force. Okay, so you will know where you're turning left and how much. Okay, that's let's say it's a two-dimensional curve. Because for dimension 3 or higher, there are other characteristics to get the whole curve. But the curvature certainly you can get in any dimension. So so once again, you can figure out the curvature of the curve by living inside the curve. Either it is a tube, or now that takes us to the next level, being our universe, which might be curved. And we don't have this luxury where somebody else looking at our universe from the fourth dimension and telling us how curved our universe is. But we could figure it out by traveling. So and that apparently that's what gravitation does to the universe. It curves it. Okay. So it is in fact not a three-dimensional curve of our three-dimensional space, but technically it is the curving of our four-dimensional time-space. So it's certainly way more complicated, but it starts right here by we are measuring things from the inside. The idea that we can measure things by being inside of that thing is certainly is the starting point, like I said, to studying the curved universe. So instead of being a little bug running through that tube, we are living in three-dimensional space, and well, we could figure out the curvature of the universe. Okay, so we're going to start the next topic next time. Functions of several variables.